All right, let's jump right in. Today, we're going to get into a pretty amazing story of transformation. I mean, we're talking about a kind of geological alchemy, where a totally common rock gets fundamentally changed into something brand new. We're talking about the formation of Wollastonite.
And this quote right here really nails the core of our story. You can think of this as a drama with three main characters. You've got your humble limestone, some really intense heat, and then the crucial ingredient, silica. The way these three interact, well, that's what drives everything we're about to see.
So this is the big question, right? How does this even happen? It's a process that goes down deep inside the Earth's crust. But you know what? The chemistry behind it is surprisingly straightforward. So let's break it down.
Okay, so to really get this transformation, first we need to get to know our starting materials. It all kicks off when two key players meet under some pretty extreme conditions.
Our story starts with limestone. You've probably seen it before. It's everywhere. Chemically, it's super simple. It's mostly just calcium carbonate, or CaCO₃. This is our raw material. This is our starting point for the whole shebang.
Now, what happens when this quiet, ordinary sedimentary rock runs into an unstoppable force from below? Well, we introduce magma, molten rock that basically acts as the powerful agent of change in this whole story.
And you gotta understand, magma is way more than just a heat source. It brings three critical things to the party. First, you've got immense heat. Then you've got these superheated fluids that creep into all the cracks in the rock. And most importantly, you have silica. That's the final ingredient we need for our transformation.
So, let's see how this all comes together. You can really think of it as a recipe for a new rock. The process is called contact metamorphism, and it's all about what happens when these ingredients get combined.
And it happens in three pretty clear steps. First, the magma makes contact. Simple enough. Second, that intense heat and pressure make the calcium carbonate inside the limestone totally unstable. It's just ready to change. And finally, the silica that the magma brought in starts to react with it.
And that reaction, well, that's the climax of our story. This is the exact moment where one type of mineral chemistry just gives way to another, and a rock is fundamentally reborn.
And here it is, the core reaction itself. So you start with your limestone, which is calcium carbonate, and you add the silica from the magma. When you apply heat, boom, they transform into calcium silicate. That's our new mineral, Wollastonite, and in the process they release bubbles of carbon dioxide gas.
So let's just recap that. We started with limestone, right? A sedimentary rock made of a carbonate mineral. Through this reaction, it became Wollastonite, a metamorphic rock made of a silicate mineral. And along the way, it released carbon dioxide gas. It's a complete chemical makeover.
So the most important thing to get here is this fundamental shift in chemistry, going from a carbonate to a silicate. And geologists have a fantastic name for this. They call it metamorphic decarbonation. The rock is literally losing its carbon to become something totally new.
Okay, now that we kind of get the chemistry, let's zoom out and look at the environment where this all happens. You can think of it as the geological kitchen where this whole recipe gets cooked up.
For Wollastonite to form, you need a perfect storm of conditions. You need crazy high temperatures, you need a ready source of silica, and you need cracks or pathways for those superheated, silica-rich fluids to travel through. And where do you find all three? Well, right next to a magma intrusion.
Geologists actually have a name for this specific reaction zone. They call it a skarn. It's that boundary layer where the hot, silica-rich magma chemically messes with the cooler, carbonate-rich limestone. It's just a zone of intense chemical exchange and new mineral creation.
And Wollastonite isn't alone in there. These skarn zones are like mineral factories, just churning out a whole family of related gems and minerals like garnets and pyroxenes. But Wollastonite is often that key indicator that this specific type of high-temperature reaction has happened.
So why does a rock that forms deep underground even matter to us up here? Well, its unique properties and the way it forms have some pretty significant implications, from our industries all the way to how we understand the planet itself. I mean, because of its unique needle-like crystal structure and its chemical stability, Wollastonite is incredibly useful stuff. It's used as a reinforcing agent in high-performance ceramics and plastics, it's a filler in paints, and it's in all sorts of construction materials to add strength and durability.
But beyond all that, this process is a key window into Earth's deep carbon cycle. Remember that CO2 gas that was released? Well, that's ancient carbon that was once locked away in limestone, being put back into the planet's systems.
Studying these formations helps scientists understand and model how carbon moves between the deep Earth and the atmosphere over millions of years, which, as you can imagine, is crucial for understanding our planet's long-term climate.
So look, if you take just one thing away from all this, let it be this sentence. This single line captures the entire process we've just explored, from the ingredients and the conditions all the way to the final products.
But here's a more poetic way to think about it. This is a story that's millions of years in the making. What began as shells on a quiet seafloor gets buried, becomes rock, and then meets a fiery intruder from the mantle, transforming completely and releasing a breath of ancient air.
And this might be the most powerful takeaway of all. When you look at the incredible diversity of rocks and minerals on our planet, what you're really seeing is the result of basic chemistry, just playing out under the immense heat and pressure of geological forces. It's that simple, and it's that profound.